Welcome back to the Graduate Summer Course. I'm Claude, your teaching assistant. Today we're going to open the toolbox you'll rely on once your code involves more than one person and more than one machine: SSH, Git, GitHub, curl, and Docker. Before we get into any of that, think about something you've almost certainly done: submitting an assignment through your school's online learning platform. You pick the file, hit upload, watch the page spin for a second, and see a green checkmark appear. And you get that little wave of relief. It's in, you can stop thinking about it. Say you catch a bug half an hour before the deadline, so you upload a second version with the same file name but different content. The platform only logs the last file you submitted and the time you submitted it. It doesn't keep the earlier version, and it doesn't keep any record of what actually changed between the two. 3 weeks later, the TA emails you, "This doesn't compile." Which version did you actually submit? The one you fixed, or the one that still had the bug? For a second, you can't even tell which problem you've got. Did you submit the wrong version, or did the right version only break once it landed on the TA's machine? Starting this week, shrugging it off is no longer an option. In the lab, several people may edit the same code at the same time. You log into machines you've never physically touched. You run code on hardware that someone else built and configured. And when something breaks at 2 in the morning before a demo, wait, which version is this? Stops being a mildly annoying question and becomes the only question that matters. This time, you need a real answer, not a guess or a shrug. That gap between a green checkmark and a real answer is exactly what this week is about. Once software development expands beyond one person on one machine, what keeps the work trustworthy, consistent, and reproducible? SSH lets you securely log into a machine that isn't physically in front of you. Git preserves a history of changes, even when multiple people are working on the same code. That is exactly the kind of history your learning platform may discard the instant you upload another file. GitHub turns that history into something an entire team can review and agree on. Curl helps you figure out why a service that should be responding isn't. And Docker helps make sure that it works on my machine also means it works on someone else's. By the end of this video, you should be able to generate and use an SSH key pair, understand what a Git commit actually contains instead of simply memorizing commands, review a pull request with a clear checklist in mind, debug a failed HTTP request layer by layer instead of guessing, explain how a container differs from a virtual machine and what each one isolates, and write a Docker file and a compose file that runs safely and reproducibly. If you haven't watched week 0 yet, do that first. The Linux basics covered in that video are assumed knowledge here. One more thing before we start. This week's course comes with labs and assignments built for you to actually get your hands on, not just watch someone else type. Come in relaxed, none of this is as complicated as it looks on the slide, and if something doesn't click the first time through, that's fine. That's exactly what the lab is for. Let's go log into a machine you've never sat in front of. Before 1995, if you wanted to log into a remote machine, you used Telnet, rlogin, or RSH. Your password went over the wire as plain text. Your whole session did too. Anyone on the same network segment with a packet sniffer could read your password character by character, no cracking required, just watching. Tatu Ulonen built the first version of SSH after his own university account was compromised in exactly that way. Someone sniffed his password off the network. SSH made 2 promises at once: encrypt the entire connection and confirm that you're actually talking to the right machine. That second promise is the one people tend to overlook, and it may be the more important one. Say you establish an encrypted connection to what you think is your lab's field gateway, but another machine has quietly inserted itself between you and the gateway. Everything you type is still encrypted, but it's encrypted for the wrong party. That machine can now read every keystroke before re-encrypting and forwarding it, and you'd have no idea. That's the uncomfortable part. Encryption alone can make an intercepted conversation feel completely safe. This kind of interception is called a man-in-the-middle attack, or MITM, and it doesn't require anything exotic. You might be using shared lab Wi-Fi while something on the network spoofs DNS, or a compromised jump host might sit between you and a robot and quietly proxy your session. Encrypting the connection without verifying who's on the other end is like carefully sealing an envelope and then handing it to whoever happens to be standing nearest the mailbox. The seal is perfect, but the recipient is wrong. So how does SSH confirm your identity without ever sending a password across the connection? It uses public key cryptography, which relies on a one-way mathematical relationship between a private key and a public key. Your private key can produce a signature for a piece of data. Anyone with the matching public key can verify that the signature came from your private key, but they cannot derive the private key or forge the signature themselves. The process works in only one direction: sign with the private key and verify with the public key, never the reverse. That's why it's safe to share your public key, even with a server you don't fully trust. The key can verify your signature, but it cannot enable someone else to impersonate you. Compare that with a password. Every time you log in, you give your password to the server. If the server is compromised, or if you enter the password into a spoofed prompt, the secret itself has left your hands. With key-based authentication, the server sends a challenge, your machine signs it locally, and the private key never leaves your laptop, no matter how many times you log in. Let's generate a key pair. SSH key gen -lowercase t ed 25519 -lowercase f tilde /.ssh/lab produces two files, lab your private key and lab.pub your public key. Here we're using ed25519 and that choice isn't arbitrary. An RSA key generally needs to be at least 3072 bits and is often 4090-lowercase 6 bits to be considered secure today. Its signing operations are also comparatively slow. ed25519 keys are much shorter, offer faster verification, and are designed to avoid certain side-channel timing attacks that have affected older RSA implementations. That's why ed25519 is now generally recommended over RSA. When it prompts you for a passphrase, that's a second layer of protection for the private key file itself. If someone steals your laptop, they can immediately use an unencrypted private key, but they still have to crack one protected by a passphrase. And remember week 0, the private key file needs hmod 600. SSH checks this automatically. If the private key is accessible to other users on the machine, SSH will refuse to use it and display a permissions warning instead of silently trusting an exposed key. Now here's the part almost nobody thinks about the first time. Connecting to a server involves not one but two separate identity checks, running in two different directions. The first time you connect to a host, you'll see a message saying that the authenticity of the host can't be established, followed by an ed25519 key fingerprint. That fingerprint is a cryptographic hash of the server's public key. It's a fixed-length summary that's effectively impossible to reproduce with a different key, so you can compare the shorter fingerprint instead of the much longer key itself. This is the server proving its identity to you. The mechanism SSH uses by default is called Trust on First Use, or TOFU. The first time you connect, verify the fingerprint through a channel other than the connection itself. You might check a lab wiki, ask someone to read it aloud, or look in your team's chat. Only then should you type yes. Once you do, SSH stores the fingerprint in ~/.s SSH known hosts. Compare this with the way your browser trusts HTTPS websites. With HTTPS, a certificate authority vouches for the server in advance. SSH doesn't normally have that external authority. It trusts the key you accepted the first time, which is exactly why the initial verification matters so much. This is where the fingerprint becomes a useful security signal rather than an annoyance. If it changes during a later connection, SSH doesn't merely warn you. It refuses to connect and displays an alarming message about a possible attack. Don't panic and delete the offending line from known hosts just to make the error disappear. A changed fingerprint often has an ordinary explanation. The server was re-imaged, moved to a new machine, or replaced by a new cloud instance. But it can also mean exactly what the warning says. Find out which explanation is correct first. Once you've confirmed that the change is legitimate, run SSH key gen-R with the host name. That command cleanly removes the relevant entry without requiring you to edit the file by hand. That was the server proving its identity to you. Now, let's reverse the question. How does the server know that it's really you? SSH copy ID -lowercase I tilde /.s SSH/lab.pub. User host logs in once with your password and then appends your public key to ~/.ssh/authorized_keys on the server. Under the hood, the command is doing something quite simple. You could append the key manually over an existing connection. There is no magic involved. From then on, the server can verify a signature from your private key against that entry and let you in without asking for your password again. The same permission requirements apply on the server side. If other users can write to ~/.sss, SSH will reject the setup. A successful connection therefore clears two separate hurdles. The host key proves that the machine is who it claims to be, and your identity key proves that you're someone the machine has agreed to trust. Compromise either side by connecting to an imposter server or adding someone else's key to your authorized keys file, and the entire chain of trust is broken even if the other half still looks fine. Typing a passphrase every time quickly gets tedious, so there's SSH Agent. It unlocks your private key in memory once per session and lets subsequent SSH connections use it without prompting you again. There's also agent forwarding, enabled with the ~A flag, which lets a machine you've connected to use your local agent to authenticate to a third machine. Be especially careful with this feature. Forwarding your agent gives the jump host the ability to authenticate as you for as long as the forwarded connection remains open. If that host is compromised, someone on it can use your forwarded agent to access other machines you're authorized to use. They cannot steal the key file itself, but they can temporarily use its signing capability. Enable agent forwarding only when you have a specific reason to do so. One common reason is to reach a machine that isn't directly accessible from your laptop, which is a typical lab setup. Say Robot01 is on an internal network with no route from the outside world. The only way in is through Field Gateway, a hardened and reachable machine with proper monitoring and logging. In ~/.ssh/config, you can define an alias using hostname, port, user, and identity file, followed by a proxy jump directive. This tells SSH to authenticate to field gateway first and then tunnel a second, independent SSH connection through it to robot 01. There are 2 separate authentication steps and 2 encrypted connections, not one connection pretending to be 2. This is generally safer than the agent forwarding we just discussed. With ProxyJump, the signing operation remains on your laptop and the connection is simply tunneled through the gateway. Once you've established trust through SSH, you can reuse that trust for other tasks. SCP-capital. P securely copies a file over SSHR, sync avz-e, double quote SSH-p, is usually better for deploying code repeatedly because it transfers only what has changed instead of copying the entire directory tree every time. And SSH-L8080: localhost: 80 forwards a port on your local machine to a port at the remote end of the tunnel. This is useful when a remote service listens only on localhost, such as a Jupyter Lab server or a TensorBoard instance on a lab GPU machine. Keep the service bound to the remote machine's loopback interface and forward it through SSH. Your laptop's browser can then reach it at localhost 8080, while the service itself is never exposed to the public network. This follows the same principle as week 0's discussion of 0.0.0.0 and 127.0.0.1. Access is provided through SSH, instead of requiring the service to expose itself to the world. Now let's move from trusting a machine to trusting a history of changes to code, which is a different kind of trust problem entirely.